Dear participants, welcome to day 4. It's a pleasure to see that we are still going strong, even if we have had many interesting sessions and many social events to attend, but I'm glad to see that many of you are still here and keen to hear today's plenary and the rest of the sessions this afternoon. So, today I'm delighted to give you a brief introduction to Professor Kling. She will talk about the very interesting topic of the social cost of nutrient pollution. In the interest of time, let me be brief about Professor Kling's numerous and outstanding achievements. She's the Professor of Environmental Energy and Resource Economics at Cornell University. Prior to that, she was Distinguished Professor of Economics at Iowa State University, where she also served as the Director of the Center for Agriculture and Rural Development. Kathy is the Director of the Cornell Atkinson Center for Sustainability. She's also, as you know, the Editor-in-Chief of the Review of Environmental Economics and Policy, which, under her guidance, has further blossomed and just received an even higher impact factor of, I think, above 7. In addition, Professor Kling is a member of the National Academy of Sciences and a fellow of a host of prestigious associations spanning social and environmental sciences. Professor Kling has made substantial contributions to the advancement of environmental and agricultural economics with both theoretical and empirical research that has significantly improved our ability to analyze difficult environmental problems. Her rigorous work relates to the theory and practice of valuing environmental goods and the design of environmental policy. Let me focus today on the practice, given that this will be the subject of Kathy's talk today. Her empirical methodological interests include the refinement of random utility maximization and discrete choice models, and their application using primary data collected often via survey experiments. She's also built an interdisciplinary research group to develop integrated land use and water quality models to provide policy guidance on the design and implementation of environmental policies in agriculture. The insights of our integrated assessment models have been applied to assess cost-effective policies to reduce nutrient loadings in local waters, both in the US and internationally. And this will be the subject of today's talk. Let me stop here. Please join me in welcoming Professor Kling. The floor is yours.
Thank you very much. While they're loading up my slides, how about a shout out for the organizers of this amazing conference? They've really done a fantastic job. It's really been nice. Thank you very much. Yep. I'll also mention that if I look a little hot and sweaty, it's because I am a little hot and sweaty. A little supply chain issue with taxi cabs this morning at the hotel. And so after waiting a long time, I decided I just better try one of those scooters. And I didn't kill anybody, and I didn't hurt myself. So, so far, the day is going really, really well. I hope we continue on that path. Okay, today we're going to talk water. And I've put to start with this picture up on the right, because it depicts something that's very important about water. Water moves. And if you're going to study damages from water or costs of controlling water, you have to think about the fact that water moves from one place to another. Unlike climate and greenhouse gases, it's also very localized in its damages. And so we have a different kind of environmental externality and problem than we have with greenhouse gas and climate change. It's a bit more analogous to some types of air pollution, but each one of them is their own sort of animal. I want to thank and call out my many co-authors, 2 of whom are in the audience. Christian Vossler and Tina Ann Darge are here somewhere. And so if I might call on them to help with some answers. It's a very large group of researchers. Christy Joliffe and Jacques Finley are both ecologists. They're limnologists, they work in rivers and streams, and they've been key in some parts of this work. Manuel Hoke, Youngji Ji, Dave Kaiser, myself, Dan Fineff, Jimmy Scher are all, like Christian and Tina, economists, environmental economists. So It's taken a lot to get this far, and we got a lot longer to go. The final thing I do want to say, when you look at this picture, keep it in your head, because I'm going to come back to this picture. Basically, what it's depicting is starting points in the way that water moves. All those red points are small watersheds, and they have a flow path that takes them into those blue areas. And I'm going to show you results that depend upon following that path of pollution. Oops. Really briefly, I'm going to talk and give you an introduction about nutrient pollution, what it is, what's happening with it in the United States. This is entirely US-centric. I'm going to give you a quick overview of our integrated assessment model conceptually, and then the various data layers, and finally get into the economics associated with estimating damages associated with these externalities in this IAM. For folks from the US, this is an anniversary. The Clean Water Act was passed 50 years ago. It was a very important act, like clean air. We were at a horrible situation with water pollution related to industrial sources. There was pictures of rivers on fire, all kinds of incredibly poor water quality, and some of it quite toxic. A goal of the Clean Water Act is to eliminate discharge of pollutants into navigable waters, like the total discharge. That was the goal. Needless to say, we have not achieved that, but we have made enormous progress in some areas, particularly industrial and municipal sources. Those sources have been the subject of direct regulation. Is it least cost? No. Is it economically efficient? No. Did it meet the goals of getting pollution out of our water? Yeah. So while it could have been done, no doubt, more efficiently, the primary focus to achieve reductions in water quality, in impairments to water from those sources was in fact achieved. However, the Clean Water Act explicitly excluded agricultural and diffuse sources. What that means is anything coming from broad land, big cropping systems and so on, are not subject to any form of regulation. Likewise, municipal golf courses and runoff from cities, those sorts of diffuse sources are not at all regulated. Instead, the policy has been to rely on so-called voluntary approaches. Now, put the little question mark there, because often when you talk to agricultural interests, they will say, well, if you pay us, we'll do it. And to me, that isn't quite voluntary. That's the notion to me of more of a pay-for-service notion, but as a result of these sets of policies, we have had huge improvements, as I said, from various industrial sources that are directly regulated, including some industrial sources of water pollution. We have not done very well on nutrients. So I'm going to spend, that was my segue into nutrient pollution. And in the case that there's lots of folks maybe that aren't that familiar with what that means, I got a Nutrients 101 slide for you. I will be using the term nutrients kind of interchangeably with nitrogen and phosphorus. These are nutrients. They grow stuff. They're needed. They're absolutely necessary for growing most anything. They are naturally occurring in water bodies, water systems, as well as the whole around us all. They're critically important components of food webs. Algae and aquatic plants feed on them. They then grow. That provides habitat and food for larger species and so on. However, too much nutrients is a very bad thing. Basically, if nutrients run off, nitrogen and phosphorus come from fertilizers and air sources, it adds too much fertilizer into the system, and it does what fertilization does. It makes things grow. It causes excess algae and plant growth, which in turn degrades food resources and habitats. It takes oxygen out of the water bodies, fresh and salt water, because as it degrades, it uses oxygen to biodegrade. There are a number of problems, illness to humans, pets, and so on, that can be a result of this overnutrient. A particularly important one goes under the term harmful algal blooms, and I'll talk a little bit about those. You'll often see these abbreviated as HABs. They actually contain poisonous substances that both humans and animals, wildlife, if exposed, can be made very ill or even die. Well, how are we doing in the US on nutrients? What do we know about it? For a long time, we didn't know very much. But happily, a couple decades ago, the US EPA started a series of snapshots of water quality done, well, basically whenever they have enough funding from Congress to do it. And what they have done is take a very statistical, representative approach. Here's an example of the sampling frame they used in the National Aquatic Resources Surveys I think this is the 2012. It takes them a long time to get the data released. These are meant to be representative of aquatic regions. They sample consistently so that they can then tell a story that is consistent over time. The latest report that came from the EPA in this National Aquatic Rivers and Streams Survey, as well as lakes, is summarized in this nice little infographic. You can steal so much stuff off the web. Isn't this cool? Like, I just had to pull it in there, make it pretty, and there's my short version of what life looks like. I was not very happy. Something like 40% of rivers, streams, lakes, wetlands in the U.S. are in poor condition regarding either phosphorus or nitrogen. And as a consequence of that, there is now extensive problems across the U.S. and frankly around the world, I'm sure many of you know, with the presence of harmful algal blooms. So in the U.S., all 50 states now experience these. There's about 15,000 water bodies across the U.S. that have nutrient-related problems. And we are increasingly seeing drinking water violations associated with these problems. And I'll drill down with a little more data on that in a minute. Here is a nice summary slide that shows you what is happening over time. That previous data was just a snapshot. But what we would also like to know, and what these National Aquatic Surveys provide for us, is what's happening over time. Oligotrophic is a fancy word for things are good. It means it's the Goldilocks, it's just right. These systems, oligotrophic systems, aquatic systems, are those that have some nutrients, but lots of oxygen. They support a lot of biodiversity, a lot of healthy ecosystems. As you can see, based on the data that they have collected from these EPA surveys, the number of good, really healthy systems has declined precipitously. And there's, in both nitrogen, or both in streams and in lakes. And these are coming from nutrient pollution. Well, that's something about the chemicals and the pollution. But we're economists, right? We care about people. What does it matter? Well, I'm going to run through a few of the main ecosystem services that this impacts before I then talk about the integrated assessment model that we have put together to incorporate and monetize these. Drinking water, first thing people tend to think of. Drinking water, we have standards, water quality drinking standards in the U.S. 10 parts per million is the maximum for nitrates. There's a lot of, which we then treat. We have to have drinking water treatment plants if they are exceeding those violations. That can be costly, and so there are costs associated with meeting those standards, a clear economic cost associated with this externality. This just provides a little bit of information about the fact that nitrates are showing up in drinking water systems. Most of these end up being cleaned. It's not to scare anybody, but they do cost money to do that, and they have to be caught in the sense that they have to know that this is coming. So population of about 10 million people have had elevated nitrate levels. Finally, and probably most importantly, 14% of Americans get drinking water not from a community water system, not from a system that is subject to those standards. Rather, they have private wells. There is no regulation of private wells. People are encouraged to test and treat if they exceed limits. We have very poor data on how well people do that, and some emerging data that there are a number of people who don't treat and are probably drinking excess amounts of nitrates. Today, I'm going to give you some results, some empirical findings only on one piece of this problem, and that's the abatement costs. As we work on this, we hope to extend further and incorporate some of those other externality damages. Maybe not a good thing to show you before your lunch, but here's a kind of grody picture, which is a second category, which is recreational uses. Lots of people, I bet in this room, like to go for hikes and walks and fish and boat, and you prefer to do it on nice water with lots of healthy ecosystems, birds, and so on. Americans in general are no different. About 13% of people in 2019 reported participating in a specific freshwater activity, which is fishing. That's 1 out of 5, just fishing. Okay, there's an enormous amount of use of our water bodies. I will be presenting some results only on lakes and lake recreation usage. Contact recreation, when you're thinking about harmful algal blooms and toxics, is different. The CDC has now documented illness and various symptoms from harmful algal blooms. You can have skin irritation. You can, if you drink much of it, you could die. I don't think there's any human deaths, but there are pets and cattle that are regularly killed because they drink toxic algal blooms. Again, I'm only going to be talking about lakes, and I'm not going to be talking about those health effects from exposure. I did note that paddleboarding is something probably a lot of people do. My husband gave me a paddleboard last year, and you're supposed to stand on top of the water, but for me it's largely a contact recreation. So I need to stay away from harmful algal blooms when I do that. All right, of course, everybody in this room knows hedonics, right? We know that people are willing to pay to live near better areas of water. And so there's about 3 million houses in the United States that are within 500 meters. And the empirical evidence we have so far suggests that that is the distance from which you can expect to see house prices capitalized. So we will be incorporating that. Again, I will only have results today on lakes. There's other stuff that we're not going to talk about here yet. I only wanted to mention this to make clear that there is such a huge set of endpoints that to do this well, we really have to learn and understand the magnitude of the damages from all sorts of water endpoints. But we're starting with what we have. This group probably needs zero introduction to the notion of integrated assessment models. The basic idea is that we're integrating economics with pollution sources and exposure and damages. This is a little picture that shows such a notion associated primarily with air. Oh yeah, look at that. If you have air pollution that comes from a factory or some given location, it leaves the smokestack and then it moves. And in that case, it's air movement, winds, and so on. That then leads to exposure, people, animals, etc., elsewhere. There are then physical effects, that's the changes in ecosystem impacts, and then there's monetization. Again, I know everybody here is very familiar with integrated assessment models. Here's a few of the most famous ones, but there's many, many more, and of course many people in this room have contributed to that literature. So I thought maybe about this time in my talk you would like a cartoon. So here's my little cartoon of an integrated assessment model for water pollution. That, you think of that blue thingy as a river or stream. Maybe it's the Mississippi River, maybe it's the Tiber, maybe it's whatever your favorite river is. And along that river, we have sources of pollution, and we have lakes and little offshoots. The sources of nutrient pollution are largely agricultural runoff, cityscapes, and some wastewater treatment. Okay, but most of it, which has largely been controlled, but agriculture and cityscapes. So that's my little farms and the town up there. A second critical piece, as I noted earlier, is fate and transport. Once it gets into the water, where does it go? How quickly does it dissipate from natural processes? So fate and transport, like in air, is very important in water. Then there are people and ecosystems that are impacted. So I put some houses, there are actually 3 little pigs' houses, down at the bottom, and another city, just for an example. And there are fish, and there are drinking water intakes all along this large watershed. And then at the very end, we monetize it. Sounds pretty simple, eh? Well, here's the progress we've made and what we're up to. In order to do that, we got to have all those baseline data layers. So I'm going to give you a brief introduction to the data layers, and then I'm going to talk about what we're going to refer to as modules, which are the damage assessment approaches that we're using. The National Hydrology Database is the core land and river stream network that we're using. That's a map of the United States, and it's a map that's focused on watersheds. That's a typical term we use in the US. You might also hear basins, and you might also hear catchments. Those are words that are used interchangeably to mean a watershed. There is data which on 3 million digitized reaches, that means all the tiny little streams. We know where they all are, and we have information about flow that we've gotten from the National Hydrology Data Set. There's 17,000 lakes and reservoirs. There are 18 different colors up there, 18 different watersheds. If you remember that picture from the very beginning I showed you, I identified one small watershed within each one of those. And so when I give you empirical results, we're going to be going to one place in all of those for me to illustrate how this whole system works. This is a map of where the lakes are. There's lots of them, all different sizes. We need, for an integrated assessment models, we need to know how much nutrients is in the water. Okay, we need to know a baseline. There's a very nice paper published in Scientific Data by an ecologist, computer science guy, Shen, and a group of authors, where they took a lot of data on nutrients. There's a huge amount of data that's been collected independently, both by EPA, STORE, all kinds of things. They combined that data, applied some fancy machine learning algorithms, and came up with their best estimate of the average sort of, I think we can kind of think of this as an equilibrium, short-run equilibrium average amount of nutrients. They did it by each time of year. We're not going to be doing that. I'm going to be using averages. But what jumps out at you from this map is big red spots is where there's high nitrogen and phosphorus. The low blue spots is where there's low of both. And then you can see the other 2 quadrants where there's high of one versus high of the other. It is spatially distinct. The U.S. has not got a similar set of problems. It is there's higher focus. So we really need to think about the spatial aspect. I mentioned that we have this routing, these digitized elements. So what this picture shows you is one of those small watersheds, which is one of those that I'll show you results from the 18. This is what it looks like. All the little rivers and streams, and we have all of that data and all of that connectivity from which to build our fate and transport model. Here's another map of that kind of movement. These are the same red small watersheds. And now you can, having hopefully understood what I'm thinking about and wanting you to focus on, here is a small watershed in one of those 18 larger watersheds. Any water, nutrients, or other contaminants in the water here will move down this set of locations. That's the path. That's the fate and transport, which we need if we're going to understand how pollution here impacts social damages elsewhere. But then we got to know where the people are. Because on the one hand, I just told you that nutrients are not uniformly distributed across the landscape. But of course, people aren't either. And as economists, we care about, at least in part, where the people are. So census tract data provides, many people have used the census tract. There's 73,000 of this. For each census tract, we know the number of people, we know the average income, education, and with new interests in environmental justice, the Biden administration has created an index called a vulnerability index, which ranks each of these, 73,000 census tracts by a series of characteristics identifying vulnerable populations. In our work, we plan to use, and if I have time, I'll show you a couple very quick results on that, but we really plan to explore so that we can think about, as we design policy, not only in a strict efficiency benefit cost analysis, which is what we tend to go to as economists, we can also then look at which populations are most impacted. Okay, so now we got the land, the water, and where the people are. So now I'm going to move to damages. And I'm going to talk about 4 components of damages that we've got some numbers for. Drinking water, lake recreation, lakeshore residents through hedonics, and ecological and local use value of rivers. As we do this, of course, we need to think carefully about double counting to avoid it, and undercounting. So what I'm going to do is give you results on each separately. If we have time, I'd be more than happy to chat about whether the degree to which these are additive or not. But for now, I'm going to present them as separate components. Okay, drinking water. Fundamentals to all of us here. What we want to know is what are the savings and abatement costs from reducing nitrogen in source water? Fortunately for us, there's a paper that was published a few years ago, Mosheim and Roboto, that estimate the marginal cost of treating for nitrate removal in large drinking water systems. They took a data set of 360 treatment plants and generated a set of marginal cost estimates that are a function of the location of the treatment plant, the original nitrate starting level, the source water intake, and the region of the country. That's great. That gives us a way to estimate costs. We take their costs and we do essentially a benefit transfer. We use those costs elsewhere. However, we don't actually know which plants treat. We don't know which ones are treating regularly and which ones would have to, on the margin, treat with more pollution. So we do what all good economists do. We make some scenarios. And one scenario we look at is, suppose, in the most extreme, all treatment plants were to treat for larger amounts of nitrogen, which is almost surely an overestimate. Another one is that a scenario is that only plants in the highest polluting regions of the country treat, which is probably a much better guess. We definitely want to do some data collection to get a better handle on this. One interesting thing in talking to drinking water treatment plants, supervisors and so on, they don't wait until they're at risk of exceeding that standard. When nitrates start to rise in their surface water intakes, they flip the switches and start running those machines. So it's an interesting economics aspect that it isn't really just, are you at 10 parts per million? These are, of course, large fixed costs. They have to anticipate, and in some cases, they have to build entirely new facilities. So the marginal cost alone doesn't capture the full cost. Okay. This is just a map of where, again, connecting people to the ecosystem service. 67% of people that get their drinking water from public water systems get those from surface water. That's the source that we'll be talking about in these estimates. This is a picture that's kind of talking through, I know it's kind of complicated, and I'm sorry, there is a couple equations, but you don't have to read them. This is actually a picture of a drinking water treatment plant. It's the largest nitrate removal plant in the world, or at least it was as of a few years ago. It's based in Des Moines, Iowa. And Des Moines, Iowa, for those of you who know your U.S. geography, is smack dab in the middle of that bright red place where there was all that nutrient pollution. So this is a huge issue for them. And this is a picture of what it looks like. So what do we do in scenarios? Well, we say, let's suppose that there's a change in loads to water, either an increase or a decrease. And then let's use our simple fate and transport model to figure out where it goes. We then know where downstream drinking water plants are. We do not know the specific location, and in fact, it's good because there's concerns about terrorism and whatnot if these particular locations are known, but we know where they are within a county. And so we can geolocate them in the sense of assessing costs to people. Then we have two scenarios. One is, are we going to assume everybody treats or just a section? We can apply this abatement cost and aggregate it up. What does that look like? Result number one, let me be very clear that this is actually, I shouldn't even use the word result. This is very illustrative. This is the first time this is put in front of you. I'm sure all these numbers are going to change dramatically, but this is the goal of what we're after, and I hope it provides a good illustration. So what is this? This is our estimate from our model of reducing the reduction in costs of treatment from nitrates if we have a 20% decrease in nitrates. Okay? That is a very large number. So this is really illustrative. It's going to take us a long time to ever get there. So again, just an illustration. Furthermore, and most importantly, of what I'd like to get across to you today, this does not include the fate and transport yet. Next slide is going to do that. It's important because a lot of work that's been done in water and other systems thinks about localized water quality. We'll talk about a proposal to improve water quality in one location, and what we really want to think through and emphasize is that that's not going to be enough in many cases. So, this goes back to that map at the very beginning. Each one of these, in this case they're blue, are the locations of abatement cost treatment. Basically, this is just pulling out those costs from the last slide, but deleting everything else. So you're just seeing those 18 small watersheds. This is the map that shows the flow of damages that includes the downstream effects. Okay, so if we do not pay attention to the downstream effects, we would be looking at estimating localized damages from additional pollution in these areas of this sort. But when we recognize that there is this important connectivity, then we can clearly see that there's a big difference. Again, all of this is illustrative. I'm sure our numbers will change, but this, I think, does a really nice job of illustrating the point. If you think about just the localized area, 16 million people are affected. But if you recognize the flow, 60 million. Okay, so there is a much bigger damage component than there would be if you don't pay attention to the fate and transport. And this is another example. This is if you only treat the most polluted places, which are all in the middle of the country, again showing exactly the same result. Okay? Drinking water, again, only the cost of treatment. Any residual health damages, which we're starting to learn that there may be epidemiological issues with nitrate levels even below the 10 parts per million. None of that is in these welfare estimates again. And of course, conceptually, they should be. Okay, lake recreation. I mentioned that there's an awful lot of people that use recreational resources in the US. I showed some gross pictures of fishing, but there's a lot of additional use, boating, picnicking. Actually, some work I did with folks at Iowa State was the most common thing people do, hanging out next to water bodies, is sit and drink their favorite beverage. So leisure is the category they click when they say what their most common activity is. So that's, people like to go by a lake or a river and have a picnic or whatever. Okay, how did we put together a national estimate of damages? Dave Kaiser, a co-author, has a paper where he looked at using the National Survey on Recreation and the Environment, which is a database of national usage of what people in the US do. And he estimated the number of trips that were reported in that survey as a function of the nutrient levels in their surrounding region as well as distance. It's basically a travel cost model at a kind of aggregate level. But that's really what it is. And then we have used that model to estimate, if you change nutrients, how much do trips change, that is the recreational usage, and then we've done a very simple benefits transfer where we're applying per value days of recreation. So Oregon State University has put together a huge database. This is very basic. This is very sort of classic benefits transfer. We hope to improve and have all kinds of plans to do so, but this provides us a starting point. This is a picture of the data, and probably the most important thing is 200 million Americans, which is about 2/3 of Americans, report every year using outdoor natural water bodies. So we know that there's a lot of usage. We don't know how valuable it is, but we know that people choose to enjoy recreation. That's missing data, so the model is fit on the rest of it, but we go ahead and use it everywhere. And that's the lakes that we will be talking about. So the estimates I'm going to show you next are for changes in nitrogen and phosphorus at those lakes. Again, I figured you needed a picture by now. In talking through the model, it's the same logic as we did with the previous model. We take a scenario, we change nutrients, we then use our fate and transport or not, and again, I'm going to show you the difference between using fate and transport and not, and then we apply this model and we get a number. That little critter right there is my daughter. Back when she was cute and loved to go in lakes. This is the same human being, and she's a little snarkier and older now. but two different types of lake recreation. If anybody knows Gabe Lade, he's an environmental agricultural economist in Minnesota. That's his son up in a Northwoods lake. And I figured when I showed you this, everybody was going to be dying to go buy one of those shark hats. Isn't that adorable? Anyway, that's recreation, all that sort of stuff. What do we find? Again, I'm going to start with just assume that there is a uniform improvement everywhere in nutrients. 20% less, in this case, phosphorus is the main driver of our recreation model. And what this takes into account is the fact that if you do a uniform change, people don't live uniformly. So this takes into account where people live, the census tract populations in which people are, and you get an estimate. What do we get? $12 billion per year. Again, illustrative, it's going to change, but that gives you the notion of what we're up to. And again, the point is it varies across different places based on both the quality of the water and where people are located. Now, and I didn't get my clicker set up right, now I'm going to show you the same kind of fate and transport. Again, just pick one of the small watersheds in each of those areas of 18. If you only look at the localized impacts, the estimate is about $127 million a year. But if you incorporate fate and transport, you end up roughly doubling that estimate. And that is completely contingent on our choice of those 18 watersheds. You could pick a different small watershed somewhere else. The downstream population and nitrogen baseline would be different, and so the estimates would be different. So again, this is just intended to show you kind of what we're up to and how the fate and transport moves. Okay, I got two more modules, and I'm going to try to do them quickly because I think you got the general idea. One of them is hedonic, so this is number 3. As I think I said before, about 3 million housing units in the U.S. lives within 500 meters of a water body, of a lake. We are not yet looking at rivers and streams. And what we do is a meta-analysis. We estimate from the existing data of hedonic values as a function of nutrients and phosphorus. For those who do benefit transfer and non-market valuation, this is a very standard kind of meta-analysis use, nothing at all novel about what we're doing here. Again, this just tells you the story of the movement through fate and transport, so I'm just going to go right on to the first set of findings. $853 million per year for a large change. Again, I want to emphasize that a 20% reduction is a big one. If we were to achieve that, it would achieve about $853 million, almost $1 billion a year in benefits that are capitalized into housing values near rivers, lakes. But again, this has no fate and transport. So what happens when we add fate and transport? Same kind of story. Oops, shoot. Got my pointers wrong. Again, if you just look at it localized, of course, not too many people are impacted in those small little regions. But if you recognize that a change in water quality here will move through to lakes and other water bodies in these other watersheds, then you can get a difference. In this case, it's not as big. $10 million, 14. But again, that's going to depend entirely on what set of watersheds you make changes in. Last one, and this I'll do again quickly. I've got a couple minutes left. A piece of value that the previous work, the 3 first modules clearly do not cover is lakes and streams. It doesn't cover lakes and streams usage, and it doesn't cover the whole idea of ecological value of diversity, of taking a walk with your kid in the evening along a lake and stream somewhere. So with funding from the U.S. Environmental Protection Agency, we and a few other folks in this room received funding to look at the value of water quality improvements in these local regional areas. There's a paper that I'm pretty sure will be coming out in the Proceedings of the National Academies soon. Christian and a whole host of us are co-authors. What we did is a study of this section of the country. This is the middle part of Iowa, and I'm sorry, of the U.S., where there's tons of nutrient pollution. That's right there in that great big red spot. And we did a stated preference study it took several years. The goal, of course, is to estimate the value of water quality improvements that includes the ecological health and potentially local use. The key thing we did was take the traditional water quality ladder, which again, those of you who have worked in non-market valuation in water will be very familiar with, and we augmented it with some biological indicators. So I don't, of course, want to take time to show you all of those details, but this gives you a notion, and this builds on work that others have done. Folks like Abatement and Brett Day have done some really nice work of this kind of thinking in the past. Basically, we showed pictures of good quality and rotten quality, and high biological diversity and low biological diversity, and we elicited willingness to pay for changes from baseline conditions to improved conditions over different geographic ranges. So that's more of an advertisement for that work than probably a chance for you to really process what we have done. So the final piece I have to show in our set of modules and results today is a scenario that looks at this willingness to pay based on the stated preference study. And it's only for the central U.S. because that was where the work was done. So this provides an estimate of the value of a 20% improvement to folks that value water quality for river, stream, local uses, and that's about $200 million a year in just this region. I'll skip this one. This is that difference between if you take into account movement, freight and transport versus not. This is a nice picture because you can sure see the freight and transport nicely. Here we've got just two local watershed headwaters. Here we have one, and the fact that there's changes here, the water flows all the way through down, and here, again, all the way through and down, and you see this much bigger impact as a result, 0.4 to 2.4. So in this case, it's about a 6-fold increase. Again, it's just going to depend on the area. Okay, I'm going to jump all the way to my last slide because I am out of time. But I want to leave you with kind of what we envision for this whole system. And I'd love to get comments and discussion. We're putting this whole beast together because we think it's really valuable and important for policy purposes. Once we feel confident in the numbers, we're going to be able to look at questions like, what are the benefits of broad landscape changes to achieve nutrient reductions? Do the highest benefits come from a few regions? We can think about targeting. Where is the most important places? We can be thinking about effective policy design. We can look at individual states and the policies that they are putting in place. We can look at who is causing externality damages to who. If you start high in the watershed, who ends up having the most damages, and what are the most important components and parts of that? Well, that's basically what I just said. So I lied. I actually had 2 more slides. My final slide is, look, we have done a fantastic job in environmental economics and air pollution. We have a lot to do there as well, but there's been a lot more effort, I think, in air pollution damages. There's big human health impacts. It's important, critically important work, but I don't think we've paid enough attention to water. So I'll leave you with the US EPA's website that says, nutrient pollution is one of America's most widespread, costly, and challenging environmental problems. So I hope plenty of folks here will step up and help provide answers and improvements to all the work that we've been doing and many people in this room are doing as well. Thank you.
Thank you, Kathy, for an inspiring talk. We have time for 3 questions, if they're quick. So we will pass the microphone. I don't see much, so make yourself visible, please. Caroline?
Hi, Kathy. Thanks for a great talk. I'm curious, so what sort of options are there under the Clean Water Act to not just regulate, but maybe start using more market-based methods, since, so now we're developing these great valuations of really the social cost of these in a spatially explicit way, or has the Supreme Court just eliminated that possibility?
Excellent, multifaceted question. So number one, states can regulate water. They have chosen to do very little regulation. They have done some. So it is completely possible for states to do it. They certainly have not stepped up in a major way to do so. Number two, I personally think that we should not be paying polluters not to pollute. I think we understand from Baumol and Oates a long time ago that there are long-run consequences that are bad if you pay people not to pollute, because then they become entrants. Like you want to produce something you get money for. Now that said, so I'm not a fan of thinking hard about payment for ecosystem services in developed countries where there is plenty of wealth. I'm talking about very much the United States, because we know that there are long-run efficiency problems that can come from that. That said, if we're not going to do anything else and we're living in a second-best situation, then yes, I hope that this kind of information can be used to spur NGOs and others to think about where to target payments for ecosystem services, where to target land purchases. Biden's 30 by 30 plan, if you take land and take it out of production in the right areas, you can get some of these benefits. So if we're going to be spending a bunch of public money purchasing and taking land out of production, we could be thinking about it in this way. As to the Supreme Court decision, it's very concerning, and I would love to get your ideas afterwards. I'm wondering myself. So I would very much like to hear what that's going to mean. Looks like David.
There has been a lot of improvement in desalinization technologies and other technologies. I know in California now they put several hundred millions of dollars to develop technologies that would lead to desalinization, and especially dealing with nitrates. How do you see incentive to technologies and mechanism of carrot and sticks that would really lead people to try to clean water? I feel that that's what will happen in California.
I don't know. I think that the Des Moines Water Works sued the local the agricultural sector in the United States, in Iowa, and that lawsuit was thrown out. Creating the incentives, one thing I hope, and we hope with this work and all the work economists do, is to recognize this is not free. There are damages. So the idea is, well, that's too costly. We can't do it. Yeah, but the cost right now is falling on people who are being exposed, and I'm particularly concerned about drinking water in private wells. And a place like Iowa in the Midwest, there are a lot of drinking water sources that are coming from areas that are heavily agricultural, and at least if we can shed light on those issues, and they're EJ issues as well. So.
To you, our tradition is, sorry, how much the EPA is listening to you. We appreciate very much EPA, but there is not a strong tradition in environmental economics and economic instruments. And do you have an opinion of what is happening in Europe? We have a strong water framework directive recognizing the polluter pays principle and a nice European topic center at the European Environmental Agency, if you have some feelings about the European work.
I think Europe is way ahead of us, and I think you have the Water Framework Directive is far beyond what we have done. So that's the shortest answer. The Clean Water Act just was very poorly designed with respect to agriculture and diffuse sources. It just, and that's what lots of the fights have been about in the Supreme Court and elsewhere, and are going to be in the courts again. So that's, EPA economists listen to us. They've been collaborators, and they're wonderful. But decision makers is a whole different thing. So kudos to the Water Framework Directive and all the work folks here have done to improve the decision making in that capacity. Yeah.
I'm afraid we're out of time for questions, but before we let you go, Kathy, we have a small present from the municipality of Rimini. It's a historical map of the city of Rimini, so
Thank you.
it's for you.
Wow. Oh.